Hey guys, welcome back to day 6 of our notes. Remember, we're in the middle of sampling distribution right now. So I know that the last video was a little intense to handle. So we're going to kind of break that down a bit today. All right. And we're just going to look at the different things that we can do with a sampling distribution. So before we get started, I do want to do a quick reminder of what the heck is a sampling distribution. Very quick, and we'll see if this kind of like quickened version of it kind of helps you understand things. But essentially, here's what's happening. There is a population. All right, so here's our population. There's all the people in our population. All right, so it's filled with a bunch of little people. There's a whole bunch of people in a population, all right? What's going to happen is we're going to pull a small sample, all right? So this is our sample out of that population, all right? And when we draw out that sample, our hope is that the sample will be a good representation of the whole population. All right. So we can check two different types of problems we discussed. We discussed either looking at proportions or looking at one that was more like numbers that we found the mean and standard deviation of. Today, we're just going to focus on proportions. All right. So let's say we found out that, I don't know, 20% of seniors are happy about not going back to school because most of you guys probably want your graduation, your prom, and all the special things. So 20% of you guys are not happy, or sorry, 20% are happy to go back to school. So in this sample, we would hope that it's around 20% as well, because our sample should be a pretty good representation of the whole population. All right. So we would hope that this sample would also be around 20%. Now, the problem is that's not always the case. Maybe we chose a really good sample this time, and there was exactly 20% that wanted to go back or was happy about this not going back to school. But what if it was on the other side and it was really far off? Like we got all people that really wanted to go back to school, so there was only like 5% in our sample. All right. So that's kind of the idea. But what's going to happen is then we're going to take another sample and we're going to find out what that one was. So let's say that the one over here was indeed 20%. It was exactly like our population, pretty much dead on. This one ended up being more around 19%. Then we went ahead and did it again. That sample ended up being around 19% as well. We did it another time, and that sample ended up being, I don't know, 22% that time. All right. And we just draw all of these samples. Now, what we talked about yesterday, the collection of all of these samples. So if we look at, let's change color here. If we look at the collection of all of these samples that I just took, all right, we look at all of those samples. That's the sampling distribution. It's all of the different proportions of each sample we did. And we talked about that if we created a bar chart of all of the like the amount of our samples that fell in each proportion, we would say that the highest bar in that would end up being whatever the actual true proportion was. So we would expect most of them to be like this guy right here, a 20% of the people in that sample saying they were happy about going back to school. So we would expect that to be in the middle, all right? Then we would expect that as we get further and further away from that number, that, what do you call it, histogram would go down like that, okay? And we said it actually ends up falling into a perfect normal curve every time we do this. And we found out that the mean of that normal curve was our proportion. In this case, that would be 0.20. All right. That's a decimal point. 0.20. And we found out that the standard deviation, also known as that guy, sigma, is going to be the square root of p times q over n. Now remember, p is the probability of success, so 0.20. Q would be probability of failure, so 0.80. And n would be however many people there were in the sample that we were drawing. So let's say in this sample again that we were looking at right here, we drew like 30 people. And that means that we drew 30 people in every sample we did, then in that case, n would be 30. All right. So we found out now we have a normal curve, all right, and that normal curve in the middle has the proportion of success of the whole population, and then the standard deviation kind of tells us how far away we go left and right. Now, again, this seems very confusing, but we're going to talk about how you actually use this. Creating the normal curve at this point is not as hard as what we've been talking about with all of this stuff. Instead, now we're just going to assume that you understand this idea of what a sampling distribution is. And instead, we're going to start using this normal curve, assuming that the mean is always p and the standard deviation is always that guy. So when we're looking at a problem, the first thing we're going to do every time is set up a normal curve, and we're going to identify what the mean is, and we're going to identify what the standard deviation is every time. And then we will use that normal curve to start answering some questions. So jumping right in, we're going to look at an example problem for what this is going to be. I'm going to do this first so that you guys feel like you can kind of see where this is going a bit more. And then we'll go back and look over some of the like requirements for when this works, how it works, and the official like slides you guys are used to seeing in the notes. But first off, let's just jump in, look right at a question, talk about this. So it says the Centers for Disease Control and Prevention report that 22% of 18-year-old women in the United States have a body mass index, BMI, of 25 or more, a value considered by the National Heart, Lung, and Blood Institute to be associated with the increased health risks. In other words, if you're 25 or more, you're fat. As part of a routine health check at a large college, the physical ed department usually requires students to come in and be measured and weighed. This year, the department decided to try out a self report system. It asked 200 randomly selected female students to report their heights and weights from which their BMI can be calculated, and only 31 of these students had BMIs greater than 25. So let's be clear about what's going on here first. First off, they have in the past tried to see like, okay, what is the BMI for a bunch of our students? All right. And they've made every student come into their office, get weighed, get measured, and then used that to find their BMI. And then they had like a good solid report of their student population. In this case, they're testing out a new one. They know that last year and the years before that, 22% of them are usually at 25 or more for their BMI. And they want to see, like, okay, if we ask 200 of them to self report, we should expect to see that same 22% of them being at a BMI of 25% or more. So what they're doing is they're taking a sample and they're going to use that sample to see if it is a reasonable way to find a sample. In other words, if it's really close to that 22%, we're going to be like, yeah, it looks like self-reporting is just as good as making them come in themselves and be measured and weighed. If it's really far away from that 22%, then we're going to say, okay, in this case, it could be possible that it's not good to do self-reporting because they lie or they don't say accurate numbers. All right. So let's first off start off 22%. That is pretty much all we need to create our normal curve. So we need two things for our normal curve. We need the mean and the standard deviation. And we know that the mean is just whatever our p is, which in this case was 22%. And our standard deviation is by following that formula we have, which is the square root of p times q divided by n, which in this case, that would be the square root of p, which is our 0.22, all right, times our q, which would be the opposite of that. So that would be what, 78.78. Sorry, I'm going off the screen there. Divided by n. Now, remember what n was. N was is looking at the actual sample size of what we're dealing with. And it said that we took a sample size of 200, all right? So that's going to end up being 200 there on the bottom. Okay. So if you actually plug that into your calculator, let me see, I got my calculator down here. It says that calculator shoots out 0.029. 0.029. All right, so we need those two things here. We need standard deviation being 0.029, and we need to know that our mean is 0.22. So in the middle of this normal curve, 0.22, and then we would go up or down by 0.029. Now, this is all the sampling distribution stuff. This is what we're going to use to now answer the question, is this 31 out of 200 a reasonable sample to begin without my trusty calculator? All right. And here's what I'm going to be doing on here right now. We know that 31 of these 200 women ended up being at the 25 or greater. All right. The problem is we're trying to compare this with a proportion. And in this case, the 0.22 is the proportion that we know. All right. So 31 over 200 isn't super helpful. So what we're going to do is just do 31 divided by 200. And that's going to give me 0.155. All right. So here's the deal. This guy down here, I want to change color, circle it. This guy down here, the 0.155, is the proportion of our sample that was 25 or higher for their BMI. We wanted that number to be 0.22. So because it's much lower than that, we are now concerned. All right. We're now concerned because we're like, okay, 15% is much lower than a 22%. So does that mean that we have to bring all these girls in and make them actually get measured with us? Because otherwise it looks like some of them might be reporting numbers that are lower than they actually are, so it doesn't seem like they're overweight or fat. All right. So the question is, how far below 22% are we willing to go before we call them a lie? This is where the standard deviation is going to come in. All right. So the standard deviation, remember, we know that 95% of people fall within two standard deviations of the original proportion. 95%. That comes from our whole 68, 95, 99.7 rule. All right. And we're able to use that to say how rare this 15.5% really is. So if I were to go one standard deviation in either direction, we actually don't care much about this direction because we're looking at a number that is clearly below the 22%. So I'm only going to go this way for right now. But the 22, how do we go to the left? Well, we just subtract our standard deviation from that number. So if I do 0.22 minus 0.029, that's going to give me 0.191. So one standard deviation away is 0.191. So how about two standard deviations away? In other words, we are moving two standard deviations below the 22%. So I will just again subtract the 0.029, and that gives me 0.162. Now, here's the deal. I know this is starting to get a little crowded, but we're done at this point. So here's the deal is in our sample, we got 15.5%. We are looking at our normal curve, and we just found out that two standard deviations below that would be 16.2%, which means our sample in this case was the 15.5 is lower than two standard deviations away from what we expected it to be. Now remember, 95% falls within two standard deviations, which means 5% falls outside of that, 2.5% above, 2.5 below. So that means that either one of two things are true. Either A, this random sample of 200 students that we selected just happened to be the skinniest girls on campus, and they were all super skinny. And it just happened to be that those were our randomly selected girls for the self reporting thing. And they were skinny enough that they fell within a 2.5% chance of happening. Or the alternative is that this sample was a bad sample, and that it turns out that having female students self report their weight and height and how they're measured, that's a bad idea. So we're going to err on the side of this would be a bad idea. All right. So again, how did we use sampling distributions in this case? We used sampling distributions by finding a normal curve with a standard deviation and mean. So we had our mean, we had our standard deviation. We created this whole thing just so that we could look at this individual sample and see how likely it would be that that would happen if all of this stuff were true. All right. So we found out that it's actually very rare in this case because they would fall outside of the two, like outside in the lowest 2.5%, which just seems unlikely. So we're going to call it a lie. So that's how we use sampling distribution. Now we're going to be able to take this even a step further in a little bit by finding out two things we've done in the past. One is instead of just saying, are we within two standard deviations, we can find the exact z score, meaning we can find exactly how many standard deviations away the sample is. Or we could also plug this into our normal PDF or CDF and find out exactly the percent that we would get a sample like this or smaller. All right. So we'll be able to take this a step further. This was just an intro to like how we would use sampling distributions in a question. All right. So now we're going to go ahead and jump back to our notes, like slides for this. Okay. So the first part of these slides is just going to go ahead and talk about when we're allowed to use this whole idea of a sampling distribution and like just some specific information about it. So it starts off here saying that when because we have a normal model, we know that 95% of the normal distributed values are within two standard deviations of the mean. So we shouldn't be surprised if various polls give us results that are not near, like exactly near it, but they're no more than two standard deviations away. So what this is saying is like, hey, if someone goes out and takes a sample in the world and they come back and their proportion is not exactly the same as ours, we should not be surprised by that. But it should be within two standard deviations because your sample will have some variation depending on who you got in your sample and who was left out of your sample. But we should still expect them to be somewhat reasonably within the range. And by reasonably, we mean two standard deviations, like within two standard deviations in either direction. Now, this whole idea that drawing a sample and it will be not exactly perfect, but at least close enough, the variation there is called your sampling error. So, your sampling error, again, is how much you would expect to be reasonably off from the true proportion with each of your samples. They also refer to this as a sampling variability. In other words, it's how much your samples will range from this value to this value based off of the information that we have. All right. Now, when is this a good model to use and when is it a bad model to use? So it talks about the fact that this model will get better and better as your sample sizes get bigger. So in the last example we just looked at, we had a sample size of 200. That is huge. So that would be a super solid good model to use. Whereas when we have like a really, really small sample, let's say we only have like 10 to 15 people, then or then we don't really have enough people to get a good idea. So let's say we were talking back at like our ACT thing. We could have ended up choosing all people that got above a 20 if we only grabbed like five people. And so that means that the ACT score we would have expected for West High would have been above a 20, which is way higher than what we expect. So the more people you have, the less likely you are to get all people in that top range, all people in the bottom range. So the larger the sample is, the better your situation will be. All right. Now, when can we do this? In order to use a normal model, there has to be two things to be true, all right? The independence assumption, and that's that the sampled values must be independent of each other, and two, the sample size assumption, which states that the sample size n must be large enough. Now, here's the problem. A lot of times we have no way of knowing if values are independent of each other, and we have no way of knowing exactly how big n has to be large enough. So what they have done is they've come up with some specific conditions that will help us satisfy those two things. So the actual things we need to check for to make sure we're allowed to use this will be our randomization condition, our 10% condition, and the success fail condition, which we will talk about more in a second. All right. So it says here that a lot of times the assumptions are hard. That's why we just assume them. Still, we check these conditions. That way we can check to make sure our assumptions are probably true. Now, let's look at what those three conditions actually are. And again, what are we doing with these three conditions? Anytime you are looking at a question or a situation like what we just did with the BMI measuring, you should be checking to see these three conditions are true in order for us to consider this to be a valid study. All right. So, first one, randomization condition. Super easy. Was it a simple random sample of the population? So did someone use a convenience sample where they just went out and chose people because that's bad and we all know that's bad? Or did they actually use some type of randomly sampling of the population? All right. Second thing, the 10% condition. The sample size n must be no larger than 10% of the whole population. Now, this one's kind of tricky to understand because a lot of times, like 10% does not seem very big, which if we're looking just at like 50 people, then yeah, 10% is not very big, all right? Because that would be what, five people out of the 50? So not being any larger than that can sometimes be an issue. But almost all of the questions we're talking about is when you're dealing with huge populations. So you're talking about thousands and thousands of people. So a lot of times it will be very easy to not hit that 10% condition. Even when we were talking about a sample size of 200, when you're looking at a whole college campus, a lot of times you're talking about like 20,000 kids. So 200 of 20,000 isn't going to break our 10% condition. All right. Next off is your success fail condition. This says that the sample size has to be big enough so that both n times p and n times q are at least 10. This is kind of a silly one, but a super easy one to check. So, in other words, it's saying you can't have the number of successes or the number of failures be so small that you would never see them in your samples. All right. So the way that they fix that is they take n, the sample size, all right, and they go ahead and multiply n by p, the probability of success, and that has to be larger than 10. On the flip side, the same has to be true for the proportion of failures. So they would take the sample size and multiply it by your probability of failure, so Q, and that also has to be 10 or larger. If both of those numbers are 10 or larger, then the third condition is met. So we're good to go. All right. Now, if all of this is true, like if it hits all three of those conditions, then we can move forward to do the type of questions we just did. So that means that any time they give you those three conditions are met and they give you the proportion, then you can use that to say, all right, then we can set up a normal curve to use for this question. And that normal curve is going to have a mean that is the proportion of success. And it's going to have a standard deviation that is the square root of p times q divided by your sample size. All right. So all of this seems, again, hopefully it's starting to be a little bit better, all right? But we just went through an actual example of how we can use this. We talked about conditions that are required for us to be allowed to use sampling distributions, and we will continue using this sampling distribution moving forward. Now, there's going to be two more videos coming up that's going to be along the same lines as this. One's going to be a short mini review lesson, and in that video, I'm simply going to go through the same example we just did with the BMI stuff, But instead of just saying, hey, all I care about is that we're within 2 standard deviations, we're going to do some review and actually try to remember how do we find the z-score for that specific one. So z-score will be the first thing we'll be reviewing. And the second one is how would we use the normal PDF or CDF function in our calculator to find the exact probability of getting a sample like that if the rest of that information were true. So we'll do a review mini video over those two things, just to look at them. And then the next major video for this is going to be doing again what we just did, but instead of doing it for proportions, we're going to do it for the other type of question, which is like the ACT example we had in the last video. And that's where we're going to have a collection of numbers, and we're going to be using the average and standard deviation of that instead of looking at proportions. All right. So that's what we have to look forward to. With that said, I really hope you guys are having a wonderful day, and I hope you are staying fit, staying healthy. Have a great week.